This is Babitha, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering. Today I am going to discuss about how to represent the small signal model of the metal oxide semiconductor field effect transistor, that is MOSFET. So while coming to the contents, here I am going to briefly explain about what is meant by MOSFET, and also how we can able to represent the small signal model of the MOSFET, and how we can able to analyze the MOSFET in small signal analysis. And in the small signal analysis, we will get the parameter lambda. So that parameter lambda is occurring due to the channel length modulation. So that's why we are also going to discuss about channel length modulation. So while coming to the MOSFET here, it is the voltage controlled device. MOSFET is voltage controlled device. Why? Because the current conduction in the case of MOSFET is due to the applied gate to source voltage as well as drain to source voltages. So if we vary these two voltages, we will get the output or drain current in the case of MOSFET. And this MOSFET is the unipolar device. Why it is called as unipolar device means the current conduction is due to majority carriers. That is nothing but which type of channel MOSFET we are considering here. Accordingly, we will get that particular carriers are the majority carriers. So due to that flow of majority carriers in the device, the current conduction will be done in the case of MOSFET. So these particular MOSFET is having three terminals: source, drain, as well as gate terminals. Okay. Actually, along with these three terminals, it is also having one more terminal, that is substrate. Okay, but generally we will combine these two terminals and make it as the single terminal, that is source. So that's why it consists of source, drain, and gate terminals for the MOSFET. Okay, so in the case of MOSFET, we are having the high input impedance, and it is having a negative temperature coefficient, and we can utilize this particular MOSFET for the switching applications as well as for the amplification. So in order to operate the MOSFET as a switching, we need to provide the biasing conditions to operate the MOSFET in the cutoff region as well as in the saturation region. And similarly, to achieve the amplification, always we need to operate the MOSFET is in the saturation condition. That is nothing but we need to provide the high VGS voltage as well as we need to increase high drain to source voltage in order to get high current, that is high drain current. There is maximum drain current we can see. In that particular condition only, we can able to utilize the MOSFET for the amplification purpose. So while we compare it with the BJT or bipolar junction transistor, even though we can use the bipolar junction transistor for the switching operation as well as for the amplification operation, but why we are moving again for the MOSFET here means, see, in the case of BJT, we are using three type of materials or three pieces of materials with different doping levels. Okay, and in this case also we will use the three type of different materials with the three different doping levels. But the thing is, construction wise both are different, and if we take the size wise, MOSFET is very less size compared to the BJT here. And power dissipation, if it is compared with the BJT, in the MOSFET it is very less. And cost of this MOSFET is also less compared to the BJT. So nowadays, in order to design any ICs, we are utilizing the FETs instead of BJTs now, in order to reduce the cost, size, as well as power dissipation of that particular IC. And in order to improve the speed of the device also we are utilizing here. So that's why even though both the devices providing the same applications, but in that we are preferably using the MOSFET because of these advantages compared to the BJT here. So these MOSFETs are available in two categories: depletion MOSFET as well as enhancement MOSFET. So in the depletion type of MOSFET, there is a channel exists between the source and drain terminals physically. And in the case of enhancement MOSFET, there is no physical channel present between the source and drain terminals. So that is the basic difference between the depletion type as well as enhancement type MOSFETs. And also depletion type MOSFET will work for all the types of gate to source voltages. That is nothing but when you provide VGS is equal to 0, it will provide the drain current. And if you provide the negative voltages, also it will provide the current. And when you provide the positive voltages, also it will provide the current. In all these three conditions, it will provide the drain current. But if we take the enhancement mode, it will operate for only VGS is equal to positive values are positive voltage. So that's why it can call it as enhancement MOSFET. We enhance the drain current if we provide the positive voltages across the gate to source terminals. But in the case of depletion type, it will give both the operations, depletion type as well as enhancement type. Depletion type means for the negative gate to source voltages, there is a decrement in the drain current. So that's why it is named as depletion MOSFET, depletion region. The current is decreasing here, so that's why it is named as depletion region. And for the positive values of VGS voltage, the drain current is increasing here. So that's why the current is enhancing or increasing here. So that's why that particular mode of operation, we can call it as enhancement mode. So that's why depletion type of MOSFETs will operate in all the regions, in the depletion region, as well as in the constant region, as well as in the enhancement region. But the enhancement MOSFET will operate in only the enhancement mode. So that is the basic difference between these two types of MOSFETs. But for the application point of view, we can utilize for both the switching as well as amplification. Both the types of MOSFETs we can utilize for switching as well as amplification purpose. So in the last session, we have seen the operation and VA characteristics of all this depletion type as well as enhancement type MOSFETs. And also we have seen how to calculate the parameters of the MOSFET, that is input impedance, output impedance, as well as voltage gain. All that parameters we derived in the last class. And in the case of MOSFET, we are not going to calculate the current gain. Why? Because we don't get any input current in the case of MOSFET. If you provide the VGS and VDS voltages, the corresponding drain current only we can expect from the MOSFET. So that's why we are calculating only input impedance, output impedance, as well as voltage gain. So because of this reason also we can say it is the voltage control device, not the current controlled device. So next we will see the small signal analysis of the MOSFET. Here I have already mentioned, so MOSFET is working with the applied voltages. That is nothing but the output current or drain current is the function of both the VGS voltage as well as VDS voltage. So the current conduction is due to these two voltages only. So in order to do the small signal analysis, we have to take the variation of these two parameters, that is VGS. If you vary the VGS voltage, how the ID current is varying. And if you vary the VDS voltage, how the ID current is changing. So these two cases we need to consider here. But before going to that, in order to make the small signal model or small signal analysis of MOSFET, always we need to operate the MOSFET using saturation region. Saturation region. That is nothing but we will get maximum constant current in this particular region of operation. So that's why we have to operate the transistor in the saturation region in order to do the small signal analysis. So here I'm going to consider the two cases to design the small signal analysis. First case is variation of the drain current with respect to the variation of gate to source voltage, and the second case is variation of the drain current due to the variation of the drain to source voltage. So in that, first I'm considering the variation of ID with respect to VGS. So in order to see this, I am taking one MOSFET circuit, okay, with the drain terminal, gate terminal and source terminal. So here I am going to see the variation of VGS with respect to ID. So that's why for the gate terminal, I am providing the DC VGS voltage and as well as AC VGS voltage between gate and source terminals. So here we need to know the notations for the DC and AC terms here. Always for the DC terms, we will use the all capital letters to represent DC terms or DC voltage, in this case gate to source DC voltage. And to represent the small signal or AC signal, we will use small letters. That is, in this case it has AC, gate to source voltage. And if you want to represent any mixed signal, that is the combination of AC as well as DC signal. So in that case, we need to represent the small letter with the subscript capital letters. So this is the mixed signal of AC as well as DC. Mixed voltage signal, that is nothing but AC plus DC. So these particular notations we are going to utilize in the small signal analysis of the MOSFET here. So in this case, VGS, capital VGS is nothing but DC voltage and small VGS is nothing but the AC voltage. And correspondingly, at drain. So here we need to provide the drain to source voltage also, but we have to maintain it as some constant value for this particular condition. VDS we are providing again DC voltage and this should be constant. So here when we apply this particular signal AC plus DC signal to your MOSFET, we will get the corresponding current, that is the combination of DC current as well as AC current. So it is ID. ID is nothing but the combination of both the AC current as well as DC current. So here we are applying the signal in this way. So this particular signal, here it is VGS, capital VGS, that is DC value, and the AC signal is this one, small VGS. So this total signal we can write it as small v, capital GS. So this is the mixed signal. So the combination of AC as well as DC signals we are applying. AC as well as DC gate to source voltage we are applying to our MOSFET in order to draw the small signal analysis. So here I have also considered the saturation region of the operation of MOSFET. So in the saturation region, what is the current we will get? We have already derived the saturation region drain current of the MOSFET that is IT equal to 1 by 2 mu n COX W by L VGS minus VT whole square. So this is the drain current in the saturation region. So where here mu n is nothing but the mobility of the charge carriers in the channel, and COX is the capacitance of the silicon dioxide layer, and W is the width of the channel, L is the length of the channel, and VGS is the gate to source voltage, how much we are applying, and VT is the threshold or cutoff voltage of the MOSFET here. So in this particular case, in the place of VGS, we are considering both the AC as well as DC signals. That is nothing but VGS is equal to capital VGS plus small VGS. So now I am taking it as the first equation. In the first equation, I am going to substitute in the place of VGS. I am substituting VGS plus VGS. So this one will become now ID equal to 1 by 2 mu n COX W by L. In the place of VGS, it is VGS plus VGS minus VT whole square. So next, just I am rearranging this particular equation as ID equal to 1 by 2 mu n COX W by L VGS minus VT plus VGS whole square. So this one is in A plus B whole square form. So I am writing this equation as ID equal to 1 by 2 mu n COX W by L VGS minus VT whole square plus 2 into VGS minus VT into VGS plus VGS square. So in this particular equation, if we compare this one with the whole term, this small VGS square. See, small VGS is the small signal. It is very less value. Compared to all these signals here, this value is very less. So we can neglect the VGS square term. So if we neglect the VGS square, our equation will become ID equal to 1 by 2 mu n COX W by L VGS minus VT whole square plus 2 into VGS minus VT into small VGS. The term is cancelled here, VGS square. Now, if we split the equation, we will get it as ID equal to 1 by 2 mu n COX W by L VGS minus VT whole square plus 1 by 2 into mu n COX W by L into 2 into VGS minus VT into small VGS. So this total term is our DC current. DC current. And here these two will get cancelled, and this current is AC current or small signal current. So this particular current is the mixed signal current. I capital D, small I capital D means this is a mixed signal current, that is the combination of DC current as well as AC current. But while doing the small signal analysis, the name itself indicates small signal analysis means we will apply only the AC signal. That is nothing but we are going to consider the only AC signal current to draw the small signal analysis. So that's why only I am going to consider the small signal current equation now. That is small ID equal to mu n COX W by L VGS minus VT into VGS, small VGS. So this is the small signal current in the case of MOSFET, and here this particular total term, that is mu n COX W by L VGS minus VT total term, I am taking it as constant. So this particular constant term I am representing with the GM. So GM is nothing but transconductance of the MOSFET. Okay, GM is nothing but the transconductance of the MOSFET. Now I can replace my ID equation with ID equal to this total term is the constant, that is the GM into VGS. So GM is equal to dou ID by dou VGS when capital VGS is constant. That is nothing but the variation of the small signal current due to the variation of the small signal gate to source voltage while maintaining the DC voltage as constant. So that one will give the transconductance of the MOSFET, that is GM. So this one we can represent with the curve, that is I am taking small VGS versus small current ID. So in this case we will get the curve in this way. So here suppose we are applying the signal like this. So this particular signal is VDC and this one is small, this one is capital VGS and this one is small VGS. So the combination of these two is the both the signals. And next the corresponding drain current we will get here it as so this is small ID, this is capital ID. So you will get it as ID and VGS. So in this way, if you provide the small gate to source voltage, there is the increment of the amplitude in the drain current. So the drain current value is increasing here. If you vary the VGS voltage, the corresponding drain current is also varying here. So now we have calculated the transconductance parameter GM and we know all the input voltages as well as output current. So from this we can able to draw the small signal model of the MOSFET. So what is the procedure for drawing the small signal model? First thing is we have to consider the three terminals of the MOSFET, that is gate, drain as well as source terminals. And if we observe our considered circuit, see here we have the voltage VGS, but there is no current is flowing between the gate to source terminals, only the voltage is present, that is VGS voltage. So that's why between the gate and source terminals just we have to represent the voltage, there is no current in this case. But if we see the gate and drain terminals, between gate and drain terminals there is no voltage is present as well as there is no current is flowing. So between gate and drain terminals there is no source is representing here, we are not going to represent any source. But if we see between the drain and source terminals, the current is flowing, the combination of the AC and DC currents are flowing. So because of that current. Because of the variation of the VGS voltage, the current, drain current is flowing in the circuit. And because of these two variations, the transconductance parameter is occurring in the device. So, between drain and source terminals, by using the transconductance, we can able to represent the drain current. See here. So, between gate and source, there is no connection, there is no current flowing in the gate and source terminals. But the current is flowing through drain and source terminals, and that is the constant current. Why? Because in the saturation region, current is constant. Once you provide the saturation region conditions for the MOSFET, even though if you vary the drain to source voltage, if you increase the drain to source voltage, it will provide the constant current. So we can represent between the drain and source terminals as constant small signal current source, that is GM VGS, that is equivalent to small ID. That is nothing but small signal current. So by using this particular procedure, we can able to draw the small signal model of the MOSFET. For that, I am considering my three terminals of the MOSFET: gate, drain, as well as source terminals. Okay, and I have already mentioned between gate and source only we are having the input voltage. Why I am utilizing only small VGS means we are drawing for only small signals, that is nothing but for only AC signals. So small VGS, and next between drain and source terminals, that is small drain current ID, that is nothing but GM into VGS. And between drain and gate terminals, there is no voltage and no current, so that's why there is no connection between the gate and drain terminals here. So this is the small signal model of the MOSFET. Once you take the variation of the ID with respect to variation of VGS, this is the first case. In the first case, we got the small signal model in this way. And similarly, if you take the second case, that is variation of the ID with respect to VDS. So in this case, again we have to consider the MOSFET circuit. But here we need to maintain the gate to source voltage as constant, and we need to provide it as DC voltage, and it should be constant. So here we need to vary the drain to source voltage, that is nothing but DC VDS voltage as well as AC VDS voltage, and we will get the corresponding drain current, that is the combination of DC current plus AC current. So in this particular case, if we see the variation of the ID with respect to VDS, we will get the curve like this. So here, if we provide the VDS voltage, this is small VDS and this one is capital VDS. This is the signal we are providing. So we are getting the corresponding current, corresponding drain current, this much. This is small ID and this one is capital ID DC as well as AC signals. So if we compare this curve with the previous curve, the drain current is more in the previous case, but here it is less in this particular case. Why? Because the drain current variation is mostly depends upon the gate to source voltage, not much on the drain to source voltage. So that's why here the variation of the drain current is less. So in this case also, we will get the transconductance parameter that one I'm taking here it as G naught, that is the variation of the drain current with respect to the variation of the drain to source voltage by maintaining the DC VDS voltage as constant value. So we are getting two parameters here, Gm due to the variation of VGS and G naught due to the variation of VDS. So with this particular parameter, if we draw the small signal model of the MOSFET, we will get it as, so before going to that, first of all we have to see the current equation. In this particular variation of the VDS voltage, that is 1 by 2 mu COX W by L into VGS minus VT whole square into 1 plus lambda into VDS minus VD saturation. So in this particular condition, this parameter is coming extra in the saturation region current, that is 1 plus lambda into VDS minus VD saturation. That is due to the effect of channel length modulation. So what is the channel length modulation? We will see, but for now I am replacing this total value with the ID saturation and 1 plus lambda VDS minus VD saturation. So from this we can also write it as G naught equal to dou ID by dou VGS. When VGS is constant, we can write it as, from this we can write R naught equal to dou VDS by dou ID. Okay, so from this we can write R naught equal to 1 by G naught into lambda. So that is nothing but one extra term R naught is adding due to the channel length modulation parameter lambda here. So with this particular consideration, we can draw the small signal model as, this is gate, drain and source terminals. Between gate and source we are applying the VGS voltage, and here we will get the transconductance GM VGS, and along with this you will get the R naught resistance here across the drain. So this is the small signal equivalent circuit if you vary the drain to source voltage. And here if we see the VDS versus IDS curve, if R naught is changing means the output resistance is varying, means the slope of the characteristics will also change here. That we are indicating here. R naught is nothing but IDS by VDS we are taking. So slope is decreasing here. If R naught value is increasing means the slope value will decrease here. So now we will see the channel length modulation. Because of this channel length modulation only, the extra parameter is added in the saturation region current. See, in order to see this one, again we are considering the MOSFET in the saturation mode. So this is the current in the saturation mode of the operation of the transistor. So in the saturation region, once the transistor is operating in the saturation region, and in that case if you increase the drain to source voltage, the charge carriers, those are electrons, are trying to move towards the positive terminal of the battery that is connected to the drain terminal. So because of that reason, the length of the channel is reducing here. That condition we can call it as pinched off. The channel is pinching off here or reducing across the drain terminal here. So if you increase still the VDS voltage, still the length of the channel is reducing here. Suppose if you take the total length of the channel as L, and the new length of the channel I am taking here it as L dash after increment of the VDS voltage. This L dash is the difference of the actual length of the channel as well as variation in the length due to the VDS voltage, that is del L. So now in the place of L in this particular equation, we have to replace with the L minus del L. So if we replace in that way, we will get it as L minus del L extra term in the saturation current. Okay. And if we simplify that, we will get it as 1 by 2 mu n COX W by L VGS minus VTH whole square into 1 plus del L by L. So here del L by L is nothing but the parameter lambda that is occurring due to the channel length modulation. The length of the channel is varying due to the variation of the drain to source voltage here. See, in this case, if VDS is increasing, the length of the channel is decreasing here. Actually, the resistance of the channel is depending upon the length of the channel here, width and length of the channel here. So here the width and length of the channels are decreasing means obviously the resistance of the channel will also decreases. Why? Because the resistance of the channel is proportional to the width and length of the channel here. So if VDS is increasing means because of the charge carriers movement towards the positive terminal, the number of charge carriers are reducing in the channel. So because of that reason, the channel length is reducing as well as width is also reducing. So we are telling that resistance is proportional to the width and length of the channel, so that resistance is also reducing here. So once the resistance in the channel is reducing means obviously the current value will be increases. So due to this channel length modulation effect, the drain current value is increasing here, and that parameter we are indicating with lambda here, lambda VDS. Why again we are considering VDS means because of the variation of VDS only we are getting this, we are coming up with this parameter lambda here. Okay. So after considering this channel length modulation into account, we will get the drain current as 1 by 2 mu n COX W by L into VGS minus VTH whole square into 1 plus lambda VDS. So again, we can write it as here VA is nothing but 1 by lambda. So in the place of lambda, we can replace with 1 by VA. VA is nothing but the early voltage of the channel. So if you replace the lambda with this 1 by VA, we will get the drain current equation as this much in the case of saturation region. So here we can able to get both the currents. That is, if you consider the channel length modulation into consider, in that case lambda value is not equal to 0. In that case we will get this particular equation. If suppose you are not going to consider the channel length modulation, in that case lambda equal to 0. If lambda equal to 0 means we will get the current as 1 by 2 mu n COX W by L VGS minus VT whole square. So we will not get this particular term if you are not considering the channel length modulation effect. And we are also not get R0 resistance in the small signal model if you are not going to consider the channel length modulation. This channel length modulation is very important concept in the case of MOSFET. Why? Because of this effect only the drain current variation will be more, as well as channel properties are also varying here. So in this way we can able to represent the MOSFET small signal model by varying the gate to source voltage as well as drain to source voltage, and also considering the channel length modulation effects. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.